Hi, good afternoon, everybody. Thank you for joining us today for the session From Blobs to Tables, Where to Store Your Data. My name is Dave Nettleton. I'm a product manager at Google, looking after some of the storage products there, and joined by my colleague, Robert Saxby, who's a big data specialist, flown in specially from Amsterdam for the event. So let's get started. So what we're going to go through today is an overview of the different products that we have in GCP for storing your data. And there's a fairly reasonable selection of those products. And so what I wanted to do, before sort of diving into the name of the product and what it does and why it's awesome, I wanted to sort of step back a little bit and go through a bit of sort of historical context as to, so where did all these products come from and why, right? So we'll go through that. We'll go through the products, talk a little bit about when to use them, what use cases, and how to think about them. And then Robert spends all his time working deeply with customers on architectures and solutions out there in the field. And he'll go through some of the sort of canonical patterns that we see that you might want to think about for your applications. And then we'll try and leave a good sort of 5 or 10 minutes at the end for Q&A. Great, so let's dive in. So let's go through the history of storage and database products. So if I go kind of all the way back, from a storage point of view, originally when you attach storage to machines, it was physically attached. So this is it's called direct attached storage. You take a hard disk, you physically attach it to a computer, and that's the storage that computer has available to it. The application, the file system, the storage, they're all on a single machine, a single device that your application runs on. So obviously, this has a lot of limitations, but it's kind of where things started, and these obviously still exist today. So direct attached storage, physically attached to the device. Obviously, you start to run into some limitations with this, like, what happens if I need more storage? What happens if I need to share my storage between servers? What do I do then? So this is where then you now need to start to think about where is my compute, where is my storage, and what role is the network playing in connecting these together? And two different models emerged here. One is a storage area network, or a SAN. And what this lets you do is it lets you move the underlying block storage off of the machine and put it into a shared piece of hardware that often offers really great performance, tiering between different classes of storage, whether it's SSD devices or hard disks. But the file system and the application is still living on the server or the client. So you can't really share that storage between different applications or between different computers because the file system that's operating it is still out there in that server. So another alternative is then network-attached storage. And in this model, one of the most common examples is something like a file share. So here the server is a file share server. You mount it over the network, so you would go into your operating system, you'd mount a directory or you'd mount a share over the network, and the file system is remote from your computer over the network. And what that lets you do is then now start to share files between many different computers. So if two clients want to operate over a shared directory in a file share, they can do it by using a NAS solution to do that. And then these are probably the most two common, and actually still today in an enterprise on-premises IT infrastructure, these are the most common forms of storage that you'll see. And more recently, object storage really started to emerge as a third form of storage for when you have really large amounts of unstructured storage, media files, or other assets that don't need the super high performance and often costly solutions that are often provided by SANs and NAS, but gives you sort of low cost, large object storage. And these solutions, so all of these solutions available in enterprises. And then as you look at the cloud, the products that you'll map to and you'll hear me talking about today for block storage, persistent disk in both standard and SSD versions, and local SSD. So this is our block storage product for attaching to VMs. For network attached storage, so for a file system, we announced as recently as last month, Cloud Filestore, which is now in beta, which is a file storage product for NAS solutions. We also have great partnerships with NetApp, EMC, Elastifile, who are also offering their solutions as part of GCP. And then for object storage, so you'll hear me talk about cloud storage as our object storage solution. Maybe one thing to note, actually, in the cloud, object storage actually sort of took off disproportionately to the on-premises use case, which is kind of an as cloud providers started to bring storage to the cloud, actually many of them started with object storage solutions, and so there's the object storage use cases are sort of really ballooned with the cloud. So this is the sort of the evolution of the different various storage products. It's all really to do is like, where's my file system, where's the data, and where's the network? All right, and we'll come back to that, the importance of the network in this a couple of times through the talk. All right. Databases. This one's a little trickier. So the world of databases was super easy for 20 or 30 years. The idea of a relational database model where you have tables, relationships between those databases, you'd run your transactional system, your banking system against that database. And if you ever needed to do reporting or analytics on it, typically these systems were scale up, actually often quite expensive, didn't necessarily store a huge amount of data because of sort of the cost and scale. And if you wanted to run reporting and analytics queries against them, you really didn't want to run that reporting query against the system that's doing your transactional records or system of record for your bank. So what you would typically do is you would go through a process called ETL, so extract, transform, load. You would lift up a copy of the data, and you'd put it in something called a data warehouse. And the data warehouse was a system specifically designed for high-performance queries that aggregated large amounts of data. So in the process of moving the data from your orders and records and customers table, you'd move it over to a data warehouse. You'd transform the data in a way that met the needs of the queries that you were going to run against it. And that's where you would run your reports and analytics from. And there's various OLAP and other technologies that came along to help accelerate that and make that super efficient. And for 20, 30 years, major on-prem, Oracle, Microsoft, IBM, built huge businesses out of this ecosystem. And for 30 years, that was good enough. And about 10, 15 years ago, a whole bunch of things started to happen that caused a lot of chaos, confusion, made choices for you all harder, right? And so what happened? Well, as the world became more connected, the internet emerged, IoT emerged, the amount of data that's getting generated and that there's an opportunity to derive value from just exploded. I mean, and if it's media assets and other things, you might put them into object storage systems and serve them. But if you want to start to do analytics over log files and other really large semi-structured or unstructured data, there really wasn't an analytics alternative for you. If you put it in your warehouse, it wasn't really super well designed for that. And it certainly didn't, from a cost point of view, it would get pretty prohibitively expensive pretty quickly. So actually, Google some time ago introduced this paradigm called MapReduce, which basically said, look, drop all of your unstructured data into just the cheapest form of storage possible, store large amounts of it, and then run jobs against that to sort of refine that data and structure it, count words in it, or look through logs for click patterns and analytics. And it introduced a framework called MapReduce around that. That was popularized into the Hadoop open source project. Companies like Hortonworks, MapR, Cloudera took that further and made commercial distributions around that. And so so for a while, there was this interesting dichotomy in the analytics industry. You know, the big data vendors would say, throw away your data warehouse. You don't need it anymore. Do everything in the big data systems. And the data warehouse folks were all very confused, going, what? I don't know. Why are they saying that? You don't need those systems. Just put it all in your warehouse. So that sort of played out over a couple of years. Fortunately, now everything probably seems to have settled down. And everyone recognizes that these are sort of complementary systems. So data lakes are great for gathering and aggregating large amounts of data. And then when you want to serve it for very particular analytics use cases or becomes more structured, then a data warehouse fits in well. So that's the analytics part of the world. In terms of storing records of data, though, this whole other paradigm emerged called NoSQL. And again, a couple of sort of patterns that have driven that were use cases where, hey, I've got devices sending me back huge amounts of data. I don't really know the columns that I'm going to have for that data in advance. They might change, or the data is going to be very sparse. You could store some of that and actually go quite a long way with a traditional relational database management system. But it sort of became clunky and a bit sort of overpowered in some areas and underpowered in other places. So for something like large key value stores, that was a whole other class of kind of NoSQL products that emerged. Another pattern is JSON documents. So if you have customer catalogs or other things where there's a sort of a hierarchical structure to the data as opposed to tabular structure to the data, it's just kind of hard, like round peg, square hole, to model that into a database. So a specific class of NoSQL databases emerged out of that. And then the other thing with a regular database is it's kind of hard to scale. They scale up pretty well. Scaling them out is really hard. So there's now at the sort of bleeding edge, and Google has some of these products, to really help customers now scale their databases beyond the traditional confines of what they've been able to do. So these have been sort of, I'll talk to some of the specifics of the products we have on this all in a second, but I just sort of wanted to take you a little bit on the journey of where these came from, and they're actually all still evolving as they go forward. So as I look across all the different products that are out there, you can see some of these starting to blend and merge. So be prepared for a little bit of that. But there's a very powerful set of products now that are much more niche to use case. It used to be RDBMS, hammer, hit, use that in all cases. There's actually more choice now in terms of what you can do with the products and the benefit you can get from them. So let me start to go through some of the products in a little bit more detail. So this is the overall portfolio that we have for GCP. So all the way, I'll start on the right. So object, file, and block products, cloud storage, persistent disk, Filestore. Our data warehouse product is BigQuery. From the database side, relational and NoSQL, Cloud SQL Spanner, Datastore, Bigtable. And then for caching in memory, Cloud Memorystore. I'll go through each of these in a bit more detail. Before I do that, though, one of the things that is another sort of trend that has emerged is this ability to separate storage and compute. One of the reasons storage and compute need to be often tied together is it's obviously just for performance, right? You want to keep if your storage and compute is co-located, you get much better performance. That often means then it's needed to be physically co-located, often onto the same machine. One of the big things that I love about Google's product lineup is we've invested so deeply in the network capability, both wide area network, like you might have heard Brad talk about in this morning's keynote, but also in data center network, the network within a data center, that our products, we can actually separate storage and compute from each other physically and actually not have it really affect performance in a meaningful way. And one of the things that this really fundamentally lets you achieve is you can scale storage separate from compute, all right? And this is a fundamentally important capability that lets you really think about and design systems in a different way, particularly in the data and analytics world. If you can just gather and store gigantic amounts of data and storage without having to size compute as you go along with it, even if you don't know how much of it you're going to use, it's a very, very powerful paradigm. And across all our products, that's one thing that we've done consistently, is separate storage from compute. And it actually means that the products that we can offer tend to then be fundamentally simpler, because we make that effectively a very seamless experience for you. Let me dive in a little bit more on the products. Okay, so cloud storage. So this is our basically our fully managed object storage system. Very classic use cases here is I want to store and serve media, so videos, images. I want to store them, serve them. I might want to backup or archive large amounts of data, or I might want to create a data lake and store large amounts of data for data processing and bring a selection of analytics products to bear on top of that. Used across a whole bunch of verticals: media, mobile, financial services, healthcare. We see this product used very broadly across the board. Some of the key features about this product. So we offer 4 different storage classes. So you can choose 2 location types: multi-regional or regional storage. And from there, you can then tier the data down into what we call nearline and cold line. So this gives you the ability to have data that's hot, available to serve immediately, but tier it down to colder, cheaper classes of storage if you don't need to access it very often. And one thing that's very unique about this product is we give you a single API across all those different storage classes. So once you put an object into Google Cloud's storage and you get an object ID, behind the scenes you can change the storage class. And you can put it in our coldest class of storage, cold line. The object ID doesn't change. And more importantly, if you ever need to access that data, your performance in terms of accessing it doesn't change either. So you basically get instant access to your cold archive data, which is very unique in the industry and a super powerful model for when you're building applications, because now you can just build your application once and not worry about the storage that it's class that it's stored in, and manage the cost and access to that storage separate from the application. So single API across all storage classes, millisecond access to the first byte of data, takes advantage of our wide area network to both bring data into the platform as well as to serve content out. So there's edge caching built in. And then another super important feature here is consistency, strong consistency. So when you write an object into Google Cloud Storage, it's immediately available for all other compute instances or analytics instances to see it immediately and operate over it. I'll talk a little bit more about strong and eventual consistency. But strong consistency is super important for analytics workloads. When you've got multiple compute instances reading and writing against a single bucket, they all see the same view of the data. And that's a pretty big deal for analytics workloads. So that's Google Cloud Storage. Persistent disk. So this is the classic, I'm running a VM, I'm using containers, and I need a disk. So the disk that we provide, it's not like a physical disk that's actually on the same server in our data centers. It's actually over the network. We create you effectively a virtual disk that you can then attach to these instances. We provide it as a single zonal product, and then we've just also recently announced a beta of what we call regional persistent disk, which actually replicates synchronously the data between 2 zones within a region, which is super important for workloads like databases, where you might want to think about high availability and failover of the database instance. So again, we make this super simple to use. We offer 2 tiers, standard and high performance tiers. With a single disk, you can scale it dynamically up to 64 terabytes. We're announcing at this event that you can go up to 60,000 IOPS on that. And again, one thing that's super interesting, super unique here is you don't need to stripe your disks to get the maximum performance out of the VM. So classic on-premises IT infrastructure, you attach multiple disks, you set up striping, RAID, and other things from an IT administration point of view to get the behavior that you want. You don't need to do any of that with persistent disk on GCP. We take care of all of that behind the scenes for you. You just create a single disk. You run all your workloads. We balance all of the operations against it. and then let you seamlessly scale it up to the maximum performance of the VM. We also have management operations like being able to take snapshots against the data. You can also take these disks and attach them to multiple VMs in read-only mode for often sharing data. So again, it's super simple, super powerful, easy to use product is what we're aiming for here with persistent disk for block storage. Filestore, so cloud Filestore. So if you remember earlier, I was talking about the different ways you might want to access storage effectively over the network and how you think about that. You know, lots of applications have been written with file storage in mind. So this is, you know, file shares, or I'm doing video and image editing in my organization. I need to share files between them, or I might be, once I've done some manipulation of various image files, I want to do some rendering in a render farm, and I need lots of compute to access those files. Or just general sort of web applications like WordPress. They all operate on this model of basically a shared file system. So with Cloud Filestore, this gives customers now a fully managed network attached file storage. Again, standard and performance tiers. We've focused very much on making it easy, simple to use from both a price and performance point of view, integrate it well with GCE and GKE, and give really just good, solid, consistent IOPS and performance. So this is now in beta. We announced it about a month ago. All right, over to the world of databases. So I wondered how far to go here. You know, acid properties, cap theorem, you know, all the kind of things you want in an intro talk on where to store storage. But I thought I'd better hit a couple of the concepts just because can't help talk about them later. So traditional relational database management system, you know, you create tables of data, and they have defined columns, and then you set constraints, foreign keys, for example, between them. Because you want to do things like if I've got a savings, you know, if I'm a bank and customers have multiple accounts with me and I want to deduct, you know, dollars from my savings account and put it in my checking account, I got to make multiple operations on multiple rows at the same time, and I want to make sure that when I do that, like the whole thing all happens together, even though it's happening across different tables. So that's called a transaction. Transactions have particular properties, ACID properties, atomic. You know, if I'm moving data between two accounts, all of those operations need to happen at the same time. Like, so it's atomic, they all happen together. Consistent, I'm guaranteed that when the operation completes, I leave the multiple tables and the overall model of the database in a consistent state. Isolated means if several operations are writing transactions at the same time, then they won't interfere with other. And durable says that, you know, once you act back that operation is complete, it really, really is complete. Even if the system dies, it guarantees to be able to recover to that point in time. So this is the sort of the classic properties of transactions. And you know, I talked a little bit earlier about, as NoSQL solutions have come along, some of the trade-offs that they've made. And one of the big things is, as I think about, you know, really wide columns or document storage, they frankly often don't need all of those capabilities, and so we're willing to make some trade-offs. And one of the most fundamental trade-offs they often make is between strong and eventual consistency. Just to kind of confuse things, this is a different type of consistency than the consistency on the left. So strong and eventual consistency means as I'm writing data in, whoever reads it is guaranteed to see the latest version. So strong consistency says every time something's written, all of the readers see the latest version of the object. With eventual consistency, it means eventually everybody will see the latest version, but not immediately. And that might sound weird, but there's some use cases where if I'm, you know, following how many people like or follow me on Twitter or something, whether it's 50,000 or 50,001, I don't really care so long as it's really fast and gets me good enough results quickly, right? So I'm willing to make some trade-offs on accuracy. But if I'm, you know, looking at banking records, you know, I don't want to, like, no thank you. I really want to know that what I'm looking at is the latest copy of the data. Thank you very much. So NoSQL systems have made some of these trade-offs, and I'll talk about the products a little bit from that context. So let me start with just the relational database management systems. So Cloud SQL is our product, fully managed third-party relational DBs. So if you're using MySQL, if you're using Postgres, if you are kind of sick of dealing with underlying storage concepts of replication, clustering, and failover, then Cloud SQL is the product for you. Gives you all of the ACID transactions at the database level that you'd be familiar with an RDBMS system, but gets you out of having to manage the underlying backends to deal with high availability, backup, security updates, gets you out of the infrastructure management and focus on the higher level values of your app. You can, of course, take MySQL and run it in a GCE VM and attach a disk to it and do this yourself if you want. But with Cloud SQL, we let you worry less about managing and keeping that service running and focus on the higher level application. So, used for all of the classic examples that you would expect a good old relational database management system to be used for. One interesting thing with most relational database management systems is they're basically what I would call scale-up systems, right? So if you want more transactions, if you want more storage, you kind of have to just keep building a bigger and bigger and bigger system. HP for many years would build bigger and bigger superdomes and other gigantic systems, basically to run really, 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 really big databases. And the reason they did that is it's really hard to scale out a database. Because as soon as you scale out a database, you end up with data in multiple places. And remember, in a relational database management system, you want to keep a consistent view of the entire database. So you've got rows, you've got tables, but the unit of consistency from an ACID point of view is an entire database. And as that scales out, it becomes very, very challenging to manage that. In fact, there's the CAP theorem basically tells you get to pick between consistency, availability, and ability to partition, and you only get to pick 2 out of the 3, right? So one of the things we've built at Google, we built it internally to deal with this problem, was a product called Cloud Spanner. And as you scale your systems up from an RDBMS perspective, imagine you want to deal with like a global inventory system. And you've got systems all around the world managing inventory, but you want a single common global inventory system. What customers would typically start to do is they'd start to manage and build and shard and come up with these complex application constructs to effectively shard out their RDBMS solution. So it would be one application, but they'd have 5 different database servers that were dealing with different parts of it, and they'd run it at the edge condition. It just becomes horrible and gnarly and messy. If you've ever tried it, I feel, good job, because it's really, really hard to do. And you can wire it together to work for particular applications, but it's just not where you want to be spending your time. So what we've done with Cloud Spanner is actually build a fully managed relational database system that can do transactions at the database level at a global scale. And the thing that we've done that's really unique is, you have to make some trade-off, right? And what we've done is, by using, this is a fascinating story, atomic clocks and something called true time, we've made it so that the trade-off on availability is so tiny that it doesn't matter from an application point of view to all intents and purposes, right? So you get a fully consistent database. We've partitioned it across the world, and we've used atomic clocks to get synchronization so tight that we can still give like a 5 nines availability SLA over this data. So this is an incredibly powerful relational database management system that we've been using to run some of the largest systems inside of Google, and really excited to see what customers are going to do with this. This was just betaed a year ago, GA now, so seeing some super interesting pickup on this one. All right, Bigtable. Okay, so that was relational database management systems. Now let me switch over to sort of the NoSQL world. So let me start with Bigtable. So here I want to store lots of records with very wide columns. So I might have tens, hundreds, thousands, tens of thousands of different columns that I might want. Not all the data is going to have all columns. It's going to be very sparsely populated. It's not very efficient to pack that into a relational database. And the thing that I care about is like the unit of atomicity. Remember, in a database, it's you got rows and tables and the entire database. In a wide column database like Bigtable, really you're only getting atomic operations at the row level, right? So you don't get foreign key relationships or anything fancy like that. What you get is the ability to write and read row-level data incredibly quickly. So this has a single-digit millisecond reads and writes, and the trade-off there is if you want to read all of that data, it's eventually consistent. So it's good for sort of big aggregate type operations. If you've been using something like Cassandra or HBase, which have really large amounts of data and you're having trouble scaling those clusters, then we have a HBase compatible API that lets you very easily move those applications across to run over Bigtable. Really great for sort of real-time analytics workloads, building out monitoring time series IoT data sets. Next, so if I now move from like, hey, I care about an individual row to I have now a document-like structure for user profiles, messaging, product catalogs. Typically, I'm dealing with sort of a JSON structure where I've got a tree of data. And what I want to deal with here is I want a certain amount of transactional support. It doesn't need to be over my entire system, but I'm going to get it over a subset of my data, and eventual consistency is OK. And this is where the current Datastore product is. And if you look at products to compare with out there, if I'm running MongoDB or Couchbase, then I'm running those clusters. This is a fully managed version of that, so now you wouldn't need to worry about managing the clusters if you switch over to using Datastore. There's a couple of other things on this page which I'll highlight now. So at this event, we're talking about how we're going to move from what we call Datastore a sort of second-generation product here. We're going to be moving to what we call a third-generation product in Firestore, so there's a little asterisk there. So you'll see we have something called Cloud Firestore announced. What we're going to do is actually we'll carry forward Datastore, completely backwards compatible within that, but we're actually going to bring even more sort of underlying power to it. So you can still use that document data model, but we're going to remove some of the restrictions that you have with it today. So you'll be able to do transactional support across the entire store, and we'll move from an eventual to strong consistency model for this as well. So remember saying earlier, the world of NoSQL database is continuing to evolve. Evolution in progress right here. The key thing here is, your data model is much more of a document-structured data model. All right, Memorystore. So great for storing all of your data. Went through a whole bunch of stores there. Now I just want to make my application go really, really, really fast. So you might use something like Redis for this already. We offer basically a fully managed version of that Memorystore, so you can now cache data in memory to give you millisecond lookups for that data from your application. Of course, it's not persistent. The persistence is in the stores I've already talked about, but super fast to accelerate a bunch of your workloads. BigQuery. So I've talked a lot about regular storage, databases, and now data warehouse. So BigQuery is our massively scalable data warehouse workload. You can store gigabytes to exabytes of data in this, running really large-scale analytics over it. I've been with Google nearly 2 years now. This is one of my favorite internal products when I got here. I was looking around and querying, like, who's using what in the product. So I write a query, I run it, 15, 20 seconds later, a result set comes back. I'm like, oh, that's cool. I'm like, how much data did I just query? Do the count, select. There's like, several billion records. I'm like, oh, okay, that's pretty cool. So this is the, really scalable, powerful data warehouse product that we have. It has an optimized columnar storage format that we manage on your behalf to just make it work really fast. You can stream data in at a really fast rate whilst querying it at the same time. We just announced in the keynote today that you can actually now build ML models directly in BigQuery without leaving BigQuery. This is a really big deal. It's really hard for people to do data science. This just makes it easier to build models so that your organization can start to leverage them right from within the tool that you're already using. So this is used across very many workloads, often as a complement to something like a data lake where I'm storing large amounts of unstructured data for serving, and for building the classic sort of data warehouse solution on GCP. And I think with that, I'm going to hand over to Robert, who will take it away.
So now we've gone through all the storages. I guess, like everyone else, we all know which storage to pick now. That's it, we're done. So if you know which storage to pick, then that was the end of the talk. If you're like me and many customers that I've worked with, and you think, oh, right, I get it now. This is what I'm going to use. And then someone comes up to you, but we try to use this product. Well, hopefully we're going to try and tackle some of that now and provide a little bit more context of how to choose which storage. And there are different use cases we're going to look at. I mean, some of these are more of a lift and shift type of use case, and some of them are going to be more of the next generation of application. Let me just grab hold of this. Or even this one. There we go. So the first couple I show you are more of a lift and shift type nature. So one use case or one expansion into the cloud that we see, even if we're not talking about applications or different workloads, is basically archiving data, disaster recovery, and just making that data available for some other use case somewhere else later. So in this particular class of use case, it's basically how do we get data from on-premise to the cloud. So the typical place where this data lands is Google Cloud Storage. As Dave pointed out, it's object storage. The durability is something like 11 nines. So you don't have to worry about backing that data up there. This is highly durable storage. So things that you might want to do here is like, okay, if I'm going to use it for an archive, how often do I actually go and access that data? So as Dave pointed out, we have different tiers for pricing there in a single API. So this makes it all good. But then the next question is, how do I get my data there? So to get your data to Google Cloud Storage, we provide utilities like GSUtil, which I'm sure some of you have already used. We have the transfer service, which is for scheduling larger loads, and you can check the hash codes that you're actually reading the right story, the right objects, bringing the right things across. And we have a whole bunch of partners out there, and I've just really put a few of them up here just to kind of illustrate the point. They really operate in the different areas, so ingesting data, helping provide solutions that back up and do disaster recovery, so getting your data somewhere, but then getting it back again as well. And obviously, in that middle category, you're also thinking, what application am I taking the data from? So you might not be on-premise reading it from object storage. You might be reading it from a NAS. You might be reading it from a database system. So how do I get that storage out? You might be reading logs. How do I get that storage out into the cloud? So I know I've got my backup off-premise now. I know I've got a disaster recovery plan. And I can start archiving as well. I can start storing maybe less data on-premise. So these are some of the things that you can consider with using Google Cloud Storage, and that typically tends to be the storage medium that's used in this case. So the next one is a bit more complicated because I've just basically gone horizontal on all the different types of storage we have here. So let's look at, actually, we're having a conversation when we were putting this together. We were trying to define what is lift and shift. And it became very clear to us that there were two actual types of lift and shift. One is the rehosting, and the other is the refactoring. Now, in rehosting, you have an application. It runs, let's say, on Windows or on Linux, and you want to run that application in the cloud. Now, that application requires storage. So if you wanted to move, for example, that MySQL instance, you want to do your operation yourself, you want to take care of the maintenance yourself because you have specific requirements or that are slightly different from what we provide in a managed service, or you've got another application that we don't have a managed service for, then you would move that application across into the cloud, run it on a VM. You could run that in a container if it was already containerized, but classically this tends to be going into a VM. And then you've got to pick what type of storage do you want underneath. So the storage, in this case, the two that you could look at are both like, POSIX block storage. You would say either a local disk, or if you want to share that amongst multiple instances, like have high availability when you're running that MySQL, if you're going to have that in two different zones, then you would look at the NAS storage that we provide. And again, there are partner solutions for the NAS as well. And that might be because you're already using that partner solution on-premise, and it would be a very natural transition to use that in the cloud as well, using the same APIs, you're gathering the same kind of metrics. So the lift and refactor, essentially, this is a kind of lift and shift story. We're saying, right, I'm going to move across, but I'm going to be using something a little bit different underneath because I need some different capability. So let me give you an example. We'll start, first of all, with HBase. So HBase typically runs on a Hadoop cluster. When you want to scale your HBase, then you scale your Hadoop cluster. You scale the storage, you scale the compute. HBase will give you something like if you, given a good key strategy, so you're not hotspotting your keys, you'll get maybe 10 to 7, well, somewhere above 10s, probably in like 60 to 70 milliseconds of latency to the first byte. With Bigtable, which would be and just for the record, HBase Cassandra are based on that original Bigtable paper. So Bigtable will give you, if you do it properly, 6 milliseconds of latency. It's atomic at the row, so you have strong consistency at the row level. You can now replicate your Bigtable into multiple zones, and then you would have eventual consistency between those two instances. But this thing is linearly scalable, which is quite a hard thing to do on your HBase cluster. And linear scalable means that if I have 10,000 IOPS, or I want to go all the way, we have customers literally in the hundreds of thousands queries per second. I said IOPS, I meant queries per second, sorry. Hundreds of thousands of queries per second at 6 milliseconds latency across their database. This thing is like, rocket fuel. That's great. How do I use it now with my existing product? Well, we actually provide a HBase compliant API. So the storage is quite different. It gives you some different capabilities. It's much faster. You can scale it linearly. But you have the same API. So that rehosting of your application becomes quite simple. Another example of this is Hadoop. So if you're moving from Hadoop, then you're using HDFS. Again, you want to decouple this. You want to have the benefit of actually being able to scale your storage independently of your compute. We would recommend using object storage. Now, there are a few limitations. Object storage is not mutable. So you can't do appends, you can't do modifications. Happens that most Hadoop workloads now just write out new files. Think about things like Parquet. That works really well with object storage. So if you want to move your Spark job, for example, to the cloud, you run it on Dataproc. The only thing you need to do is to basically run that job on Dataproc and change the HDFS prefix with GS. And now suddenly you're able to use that object storage. You're able to get much better throughput. You can have different workloads looking at the same storage. So you gain some extra benefits there. But there is a slight rehosting again because you're changing from HDFS to object storage. Things like MySQL. So you could kind of say this is a little bit more rehosting, but we're going to take the management away. So that's where the difference comes in now. You would find, for example, your interface for MySQL or Postgres for Cloud SQL is the same if you were running it yourself, but we've taken care of a lot of the operational part, the backups and all this kind of stuff. So the rehosting part there is doing less work. Sounds terrible. And the next one is Redis. Again, it's a very similar kind of thing. The rehosting part is that we're taking away some of that operational overhead. So coming back to this slide, because I think this is, as Dave pointed out, and as it was clear from my examples there as well, this is what makes Google really special in terms of infrastructure. That network in between, within our data center, is 1.3 petabits. That means 130,000 machines talking to each other at 10 gigabits per second. That's like really, really fast. That means we can consider storage which is not local, effectively local. So whether you're attaching a disk to a machine, or you're using object storage, or you're reading data from BigQuery, you're basically doing that processing part separate from where you're storing your data. So multiple workloads, looking at the same data, you can scale out the storage independently from the processing. Now, where this becomes really concrete is, for example, let's say I need two capabilities. So I have some data, and I want to make that data. Let's say I'm creating recommendations for people. Now, I have two use cases. One, I want to be able to serve those, those recommendations as fast as possible. Now, I could choose to have those in Memorystore. I could choose to have them in a key value store like Bigtable, where I've got random read-write access and also very low latency. But let's say I have another use case as well, where I want to do analytics. So I want to kind of look at all the recommendations that I've actually generated, and I want to see how they're changing over time, all this kind of stuff. Well, in that case, it might be good to have them in columnar storage, because then I can do, big, massive queries and aggregate things and just select the column I'm interested in instead of selecting the whole row of data. So I would store it in BigQuery. If you look at cloud, you look at the cost of processing, you look at the cost of storage, storage is generally cheaper than processing. So it makes sense to store this data multiple times. Now, if your use case is ad hoc, you might say, well, I don't want that. Well, then something like BigQuery provides federation to Bigtable. If your use case is, I need to run lots and lots of queries and I want them to be really fast, then you would store it in both places. So then you start to think about, how is that pipeline that's actually provisioning that storage? How can I provision two sets of storage? So in this first one, in this big data and analytics use case, we're going to look at two types of data coming in. So both events, so this is kind of streaming data, batch. Now, your processing could be with Beam in Dataflow. It could be through Spark, and you're running on Dataproc. I'm giving you options here. There are more. The point is, you can then go and choose where you store this data as well. So you could be having your batch and your streaming data coming in, you're processing it, and the next thing you're saying as well, I need to serve it up quickly, so I will move it across and make sure it's available in Bigtable, that top one in the middle there. I need to run my analytics, so you make it available in BigQuery. Actually, there's a whole bunch of data here I just want to archive because, I want to see how it's created later, or it's not in a structured format yet. I would need to change, change data types or clean the data a bit more to get it into BigQuery. Well, then put it in Google Cloud Storage. From there, if you were going to query that data, well, BigQuery is native, so you would have like native storage. Your querying is going to be optimal. The federation to the other types of storage. And then from that, you can go and visualize it with a whole host of different applications as well, or run your models, or whatever it is that you're trying to do there. Another example I want to give is like a modern scalable e-commerce. Now, you can take away the word e-commerce here and just basically put any kind of application that you're trying to scale for like internet scale. This is how we would kind of approach, and this is really kind of takes benefits of some of the things that Google can provide you. So for example, our cloud load balancing. Our load balancing is global. We get great latency on that. It will basically allow you to go and move to route the traffic to the right zone. You saw earlier in the presentation today, like how many points of presence we have. Our CDN. So if you've got data in your bucket, which in Google Cloud Storage, and you want to serve that up on your website, you can put our CDN in front of that. So it's caching it on our edge so we can serve that up to your customers as quick as possible. And then let's take, for example, the other type. So the other things that we might be doing there is having microservices, or running on Kubernetes, for example. And we might want to have a backbone, like a database, a strong and consistent database that will scale with that application, could also be globally available as well. So another point about Spanner, not only does it scale horizontally, you can also run this globally. That's what we do for things like AdWords bidding, for example. Another example, like Spanner underpins so much of what we do. If you look at Google Cloud Storage and you use that API to list the items in the bucket, that metadata, again, is stored in Spanner. That's a global product. So if you run a command and say, what data do I have in this bucket, you won't expect to see any lag in getting that results back, and you expect to see a consistent result. So you could use something like Cloud Spanner in your own application and support multiple microservices running in multiple zones. The load balancer directing you to the right microservices closest to you to reduce the latency, and having a strong, consistent data model behind that. And you may have things that you want to put to get even faster to your customer. So Spanner will give you, in the tens or the low tens of milliseconds of latency. Maybe you have things that you want to serve up in your application even faster than that. So sub-millisecond. User sessions might be an example. You might have stuff from a product catalog that you really want to get out as quick as possible. And for that, you could use Memorystore. So hopefully it's a very high-level architecture. Gives you an idea just how you would piece some of these things together. So the last thing before we take questions, and I realize we're running out of time, but I will wait out, so I'm sure Dave will as well, to answer any questions you have, is, OK, which storage? We've gone through a few examples. We have examples of this on the website, and I kind of went all OCD on the aeroplane over here, as you can see. So something like this should only take an hour to create. But when you want to fit it all on the screen and you move it from left to right 100 times, then you can kill at least 2 hours on a transatlantic flight. But hopefully, I'll just leave this up on the screen as we wrap up. But we've spoken about all of this today. And it's kind of, this is not the definitive answer. This is a guide, a decision tree to help you kind of work out which storage to start looking at. You'll see, for example, one storage here, Bigtable, you'll see in multiple places. One of the questions I get asked about Bigtable and Spanner is like, which one should I use? I should use Spanner now. Because like Spanner is just like Bigtable, but then has strong consistency over multiple records. Well, yes, it does. It has strong consistency over multiple records, over multiple tables. With that comes a lower latency. Higher latency, wow. So if you need a very low latency, and you are only interested at the row level, you could consider Bigtable. So these are the kind of things that you could think about. OK, and the rest of the questions we will take outside, so the next speakers can have the room.